In section 2.4, we'll be looking at limits. The easiest way to determine the limit is from a graph, so that's where we're going to start. Then we will look at how to find the limit from a table of values. And then what we're working up to is just finding the limit from a given function. So first of all, let's look at some graphs. These are the odd problems out of your book on page 111, I believe. And so the easiest thing I want you to think about is, want to ask yourself, what is the value of y getting close to as x is getting close to a given value? Not equal, although sometimes that is the same, but what it's getting close to. So number one, we're asked, what is the limit as x approaches negative 2 of f of x? Now notice what the book has done is it says here's negative 2, when x is negative 2, y is positive 3. Alright, that's what it equals to. But what about really close to negative 2? If I get right up next to it, what is the value of y really getting close to? And you can hopefully see that that is 3. Now, f of negative 2, when x equals to negative 2, it was also 3. So sometimes those are equal. And the reason why is on this graph there were no holes or jumps or asymptotes. It's a nice smooth line. So let's look at problem number 3. We have a nice smooth line except for we've got this little open circle here and a dot. So the function when x is 3, y is 4, it's that dot. But we want to know the limit as x approaches to 3, meaning get really, really close. So if I go on the other side of 3 and I go up to the line, on the other side of 3, and I go up, when I say go to the line, I'm going to the graph, the function. What is the y value getting close to? It is also getting close to 3. You will see that this book's kind of stuck on 3. Right? Now notice, those are not the same. That's okay. But when x equals to 3, y equals to 4. But as x is getting closer to 3, y was getting closer to 3. Okay, look at problem number 5. Again, you will notice that there is a hole and a dot. And so we're looking at the limit as x approaches to negative 2. Now when x equals to negative 2, y is equal to positive 2. That's that dot right there. But on either side, really close to negative 2, I go up to the graph. It's a little bit less than 3. That looks a little bit greater than 3. Again, the limit as x approaches negative 2 of my function is positive 3. So again, not equal to it, and that's alright. Now number 7, there's not just a hole, there's just a huge gap. Alright? So, I believe this is an open circle and that's a filled in circle. So the function when x is negative 2 is positive 2 because of that filled in. But if I go a little bit less than negative 2, then I have to come down here, and that's that y value. If I go a little bit bigger than negative 2, I have to come up here, and that's this y value. Are those y values even close to each other? No, it is not. So we would say the limit does not exist. They're not even close to one another. Alright, so let's look at these two problems. Building a table of values. Alright, so first of all, if I were to just plug in 1 into the function, you would get 1 over 0, which is undefined. But if I go to my calculator and let x be all these values that are really, really close to 1, what would I get? Well, I'll go to my calculator. I think that's 100, 10,000, Okay, notice that even though x was all very, very close to 1, are these y values close to each other? Not at all. So we would say the limit does not exist. DNE does not exist. And if you would know why if we were to look at a graph of that function, it would look like this. Here's 1, and the graph would be going way up here, and that's because there's an asymptote, and so the y values just get incredibly huge all around 1. Right? Let's look at problem number 9. Alright, so this time we want x to be close to 2. So notice we've selected values awfully close to 2 but not equal to 2. Right, so again I'm going to grab a calculator and evaluate all of those. Okay, so as I let x be really close to 2, look at my y values. Are they circling around a particular number? I think the limit is 5. Okay, well let's see. If I have f of 2, if I actually just plug in 2 for x, I would also get 5. And that's because this graph doesn't have any jumps or holes or anything. In fact, it is a parabola, and when x is 2, y is 5. Right? So that's how the graphs go together with these limits. Okay, so now, how do we find just the limit of a function? Well, the easiest way is just substitute the given value of x into the function. Right? So one example is if you have a constant. There is no x. The limit of 5, x is equal to negative 2. What are they saying? Well, what this says is that y equals to 5, or f of x is equal to 5. And if you remember what that is a graph of, it is a horizontal line of y equals to 5. No holes or no jumps. And so it doesn't matter what x is equal to, what is y always going to equal to? It's going to equal to that number. So the limit as x really approaches anything of a constant is just the constant. Right? So let's look at a line. Well, if you were to look at a graph of a line, you would recall that this is the same as y equals mx plus b. So we'd have a negative 1 here, and we go up 2 over 1. It would look like a graph. And no, you do not need to graph it, just trying to show you what these come from. And so as x approaches 1, right, when x is 1, what is the y value? Since there's no holes or anything, the easiest way is just to plug in, again, substitute the given value of x into the function. So 2 times 1 minus 1 is 1. That's the limit. Alright? A quadratic is a parabola. There's no jumps or holes or anything. So again, I'm just going to plug in 3 for x. Let's see, I think that's equal to 31. And that's the limit. Okay, you don't have to know that that's a quadratic or anything. Just know you plug in the value of x. Right, so this is a rational function, meaning a fraction. So again, I'm just going to plug in 1 for x. And I get an answer of 1/2. Okay, so that's nice and simple.